Welcome. Today we're looking at ending the AI embodiment tech trap and asking how ambimorphic autonomy could assist in leveling the playing field against autonomous swarms and be more efficient in how we integrate AI and automation into human society. For example, modern counter-robotic warfare has hit a fundamental structural limit. Traditional defensive systems, built on fixed-point defense networks, single-mission quadcopters, and static turrets, are inherently reactive, rigid, and resource-asymmetric. When forced to defend against multi-domain autonomous swarms operating at machine speeds, platforms that cannot instantly adapt their physical shape or operational logic become liabilities. Is an ambimorphic autonomous defense a better solution? We must consider that an integrated hardware and software architecture that levels the playing field by enabling real-time, dynamic morphosis across physical geometry, kinematic motion, and dual-state algorithmic logic provides several advantages. Let's explore how ambimorphic systems for defense can eliminate defensive lag, shield human operators, and turn rigid vulnerabilities into adaptive survival assets. Conventional defense relies on isolated, specialized assets. Fixed-wing drones for high-speed intercept, quadcopters for loitering, and UGVs for ground security. Ambimorphic platforms collapse these silos into variable geometry, multimodal hardware. In dense urban terrain, the platform can collapse into a quadruped or rolling configuration to reduce signatures and conserve power, then reorient thrust geometry for instant vertical takeoff. Furthermore, by dynamically altering wing sweep, shifting internal center of gravity, and articulating thrust vectoring nozzles, the platform executes non-standard maneuvers that break the tracking parameters of incoming strike algorithms. Hardware morphosis is ineffective without software capable of concurrent dual logic processing. Traditional automated systems force a sequential choice. First, jam or shield, then reacquire and attack. Ambimorphic software engines execute both operations concurrently inside a unified compute stream. The defensive vector continuously calculates evasive paths and active shielding, while the offensive intercept vector simultaneously computes zero-lag strike paths. If a unit suffers sensor degradation or damage, it shifts to a passive relay node while adjacent nodes immediately assume kinetic intercept vectors, self-healing the network without command bottlenecks. At the squad level, machine-speed defense must protect human operators without overwhelming their cognitive capacity. Ambimorphism translates directly to context-adaptive AR tactical interfaces for dismounted personnel. The operator's field of view receives a dual-layer tactical overlay, the defensive funnel, a dynamic visual guide directing physical movement to evade strikes, and the offensive reticle, providing lead angle targeting for manual engagements. When threat velocities exceed human reaction limits, under 200 milliseconds, the system automatically triggers localized countermeasures like micromunitions or RF bursts, while keeping the primary sight picture clear. At the squad level, machine-speed defense must protect human operators without overwhelming their cognitive capacity. Ambimorphism translates directly to context-adaptive AR tactical interfaces for dismounted personnel. The operator's field of view receives a dual-layer tactical overlay, the defensive funnel, a dynamic visual guide directing physical movement to evade strikes, and the offensive reticle, providing lead angle targeting for manual engagements. When threat velocities exceed human reaction limits, under 200 milliseconds, the system automatically triggers localized countermeasures like micromunitions or RF bursts, while keeping the primary sight picture clear. Deploying true ambimorphic autonomy requires solving three primary engineering challenges. First, microsecond state synchronization. Physical geometry shifts alter stability, requiring kinematic control models to compute continuous spatial derivatives in real time. Second, deterministic AI guardrails. Deep learning outputs must be bounded inside rigid, physics-based mathematical guardrails to prevent erroneous kinetic engagements. Finally, power-dense actuation. Dynamic geometry demands high-torque, ultra-lightweight actuators capable of sustaining extreme G-force transitions without rapidly draining energy reserves. In conclusion, when considering ambimorphism as it applies to defense, the ultimate significance of the architecture is the elimination of the static vulnerability trap. By integrating dynamic physical form, concurrent software execution, and sub-second human augmentation, ambimorphic systems shift counter-robotic defense from passive survival to proactive machine-speed protection, ensuring human forces retain operational dominance against increasingly automated threats. So how can we apply this to our manufacturing environments and embodied AI integration to society? Adaptive work cells have been in place for years, proving to us how and when specialized robots can be practical, economical, and efficient solutions. There may be some tasks where direct mirroring of human anatomy makes sense based on environmental or functional constraints, but from what we've already learned in engineering and manufacturing, the human form does not always provide the best mechanics. Sure, it's fun to watch and makes us feel more comfortable, but is definitely not typically the most optimal solution from a cost and reliability standpoint. Where everything changes is in defense and rescue, when you need to bring instant intel, responsiveness, remediation, and lethality all in the same package. So should we stop mass-producing specialized defense like the US, China, and every other country is already doing? No, we can't, but it's safe to say that whatever country is at the forefront of ambimorphic dense autonomy will be more than just ahead of the curve. Thanks for your time today. I hope you enjoyed today's content and look forward to your comments and seeing you at ScienTech4U on YouTube.